One powerful form of reasoning is called analogical reasoning. And analogical has the word analogy or analog in it, meaning you have some piece of knowledge that you can then use and transfer it to some new sort of problem situation and see if you can apply the analogy and if that will help you to actually solve whatever the problem is that you're trying to solve. Now, this is by necessity a knowledge rich kind of problem solving, because if you don't have prior knowledge, you can't use analogies because analogies are forms of prior knowledge. One example of where analogical reasoning really made a tremendous difference was in understanding the structure of atoms. And people for a long time had been trying to understand how electrons and neutrons orbited around in atoms and how exactly that worked and how they were structured. And they were stuck in this problem for a long time until a physicist by the name of Rutherford realized that maybe the model of the solar system, where we have the sun and then the planets orbiting around the sun, that model could be taken and applied to the structure of atoms. And as soon as that insight was gained, indeed, it turned out that the nucleus, the core of an atom, was actually very similar to the sun in many ways, and that electrons and protons and neutrons orbited around the cell nucleus in very much a similar way as planets orbited around the sun. So that is one example of analogical reasoning, where of course that couldn't have been resolved if Rutherford wouldn't have had knowledge of the solar system. So analogical reasoning is, if you want to think of it structurally, a situation where you transfer a known solution to one problem and then transfer it to a new problem domain and see if it then applies and actually helps you to solve the problem. So it's been very important in the history of science. As I said, a model of the solar system actually helped the development of a model of the atom. Now, this has been studied, of course, to see how this works. And psychologists, again, we want to know how people solve problems and how people reason, because if we can better understand it, we can perhaps create situations that are optimal for problem solving and reasoning. And that would be great. One such problem that's been used in these studies is what's known as the radiation problem. And the radiation problem is the following. Imagine that there's a patient who has some inoperable stomach tumor that can in principle be destroyed by some sort of rays. The rays, however, will destroy any healthy tissue in the body that it has to cut through to get to the actual tumor. So imagine there's a tumor somewhere in the middle, there's healthy tissue surrounding it, you can send rays through that then destroy the tumor, but unfortunately they would destroy the healthy tissue as well. Now, how can we destroy this tumor without affecting the healthy tissue? Is the question. And what they do in this problem is the following. They let people sit on this for a while, and then depending on which experimental group people are in, they're then giving some sort of analogy to this problem and then see if they can kind of dissect the core principles from that analogy and then apply it to this particular radiation problem. So one such analogy is the following. Think about Manhattan and how busy it is in Manhattan. There's a very high concentration of people in Manhattan. And that concentration is higher than the people in the surrounding areas. How do people get into Manhattan? Well, some people take the path, some people take the Holland Tunnel, some people take the Lincoln Tunnel, some people take the Brooklyn Bridge. There's many different ways in which you can get into Manhattan. So even though any of these individual methods of transport has a high volume, but not as high as the number of people in Manhattan, right? In Manhattan itself, there's a lot of people. We can see this as an analogy to what we can do to get a high concentration of radiation at the site of the tumor without having a high concentration of radiation at other places where the healthy tissue is. And if you apply this analogy, it's the same. There's multiple entry points into Manhattan, And even though none of these entry points themselves are super, super dense, when they intersect at Manhattan, then actually their concentration becomes very high. There's lots of people in Manhattan. So maybe we can do the same thing for the tumor and the healthy tissue. What if rather than one big ray of radiation, we spread that out into, so let's say 20 different small rays of radiation. We send that radiation in from different angles, right? So 20 different entry points with lower intensity, and we make that they happen to intersect exactly where the tumor is located. And now if we do this, it will destroy the tumor and it will actually leave the healthy tissue intact. So they've done this in studies where they give people this problem, and then in one group they give them what's called the general story, which is very similar to what I just said about Manhattan. The story is the following. Imagine you're a general, you're trying to attack a city. However, if you approach the city with your military from one direction, then of course the opponent will see it. How can you make that this city becomes under siege without revealing your location by having such a large volume outside of the city? Well, again, multiple entry points, right? So you could split up your whole army and then have different approach angles, and then they all intersect where the city is. So that's the analogy story that people were being given. And then you can look, okay, if now people have been given this analogy, what percentage of people ends up solving this problem? And you see, in a control condition where they weren't given any analogy, some small percentage, about 10% or so, just solves the problem itself. 90% doesn't. But in the group that was given the general story, or the Manhattan story for that matter, right, you see that still a small percentage doesn't solve it, about 70 or 25% or so, but the other 75% ends up solving it either without a hint, which means for 40% of people they may actually have realized there was some sort of analogy going on, or another 40 or so percent after they're being told this may be an analogy that you can apply to the radiation problem. So you see here that analogies, when they're productive, can really help in problem solving. Now, what happens when we use analogies? One approach to this, one way of thinking, is that there's a couple of sub-processes. First of all, we got to retrieve some piece of knowledge and put it from long-term memory into our working memory, and then see if that actually is a piece of similar knowledge. So first is retrieval, then there's mapping. We identify linkages between the source, the knowledge that you already have in long-term memory, and the current problem that you're working on. Then we evaluate whether the analogy is going to help or not. If it is going to help, we think we're then going to abstract something about the structure of the known solution and see if we can apply that to the new problem. So the structure of many people in Manhattan means many different entryways. Now apply that many different entryway structure to the tumor problem, and we see if that actually solves it. And then if it solves it, we can make some predictions about what should happen in the new problem if it were similar to the analogy that we retrieved. So there's these 5 steps involved here. Now, of course then, how well this is going to work depends on their true similarity. So for example, if we think about computer viruses and biological viruses, computer viruses are obviously not that old. And there was a time where we knew a lot about biological viruses and we didn't know anything about computer viruses yet. In fact, there wasn't even a term for it. Nowadays, we have the term computer virus. And why is that useful? Well, you can think, in what ways are computer viruses analogous to biological viruses? There's a couple of similarities. So first of all, both of them are contagious. Right? Your phone, your computer can get infected by a computer virus in the same way as we can get infected by a biological virus. Both are self-replicating. They can actually exist in one person or exist on one computer and then replicate themselves so that they now exist also in a new person or on a new computer. And then both of them are damaging to the host. Computer viruses can destroy a computer. Biological viruses can make people very ill. So computer scientists use this analogy to then try to see if they can come up with what you could call, quote unquote, a vaccine for computer viruses, or something that we now know as a firewall or a virus scanner, any of these kinds of things. So when we want to see if this then works well, you really have to look at the depth of similarity. So there's 3 types of similarity between problems that affect analogical transfer. So first of all, is there something that's superficially similar? We can think of this as just general, like broad details being common for both problems. So for example, in the case of computer viruses and biological viruses, both of them involve some sort of virus. That's fine, but that's not terribly useful yet. Now let's look at the structure of the problem and the structure of the similarity. In that case, the main causal components are shared between the 2 problems. So again, when we talk about computer viruses and biological viruses, well, both of them are, as I said, self-replicating, both do damage and so forth. So structurally, they seem fairly similar. Just like the general or the Manhattan story or the radiation story are structurally similar. Now the last one, the deepest one and the most useful one, is if there's also procedural similarity. If the way in which we have solved a known problem is similar to the way we can solve the new problem in terms of the procedures that we need to apply. If that's the case, then now actually we have a very good analogy and it will actually help us solve the next problem that we're dealing with.